Okay, I'm continuing to work through the 2015 AP Physics 1 free response questions. And I've done all problems 1, 2, 3, and 4. They're in a playlist. You can find all the problems down below. I also did a video going over the equation sheet. So I just thought I'd do this for fun, just to see what it's like. I've never taken the AP Physics exam. And maybe I'll do another one. I don't know. We'll see. So I haven't looked at this beforehand, so I'm coming at this fresh. Let's just get to it. 13-minute time for this one. That's what it says. The figure above shows a string with one end attached to an oscillator and the other end attached to a block. The string passes over a massless pulley that turns with negligible friction. 4 such strings, A, B, C, and D, are set up side by side. Right there. That's the top view. I assume that's the top view. Each oscillator is adjusted to vibrate the string at its fundamental frequency, F. The distance between each oscillator and pulley, L, is the same. The masses of each block is the same. However, the fundamental frequency of each string is different. Okay, fine. Fundamental frequencies. The equation for the velocity of a wave on a string is V is Ft divided by the linear density, m over L, where Ft is the tension, m over L is the mass per unit length. Cool. What is different about the 4 strings shown above that would result in their having different fundamental frequencies? Okay, so I guess we should start off with what is the fundamental frequency. So if I oscillate this to make a standing wave, and I have a video about standing waves that I really like, but it's a little advanced. It's not really AP Physics 1 level. If you want that, comment down below and I'll show it to you. But if I have a standing wave on a string, what happens is I oscillate the string and I get a node in the middle and nodes at the ends and an antinode at the middle. So this thing just oscillates up and down. And if you notice, this is half of a wavelength. Because if I went all the way over here, that'd be 1 wavelength. So lambda over 2 is equal to L. That's true for the fundamental frequency. I also know V equals F lambda is true for waves, right? The velocity of the wave is F lambda. And down here, I know that's equal to the square root of Ft, the tension, divided by m over L, the linear mass density. So this is the equation that I have, right? So right here, if I have a fundamental frequency, I know that. I know lambda, right? Because this is going to be, let's actually write this out as, I'm going to put in for lambda. So I have F, I'm going to solve for F. F equals 1 over lambda, which is going to be 2 over L, times the square root of Ft over m over L. I don't like writing that improper fraction. Okay, so what would change? What could I change to make these different fundamental frequencies? Well, I can't change 2. I can't change the length. I can't change Ft. So the tension in the string, if you look at this block right here, it has a gravitational force, mg, pulling down, and I'm just going to call it T, pulling up, and those are equal if that stays at rest, so that the tension is equal to the weight on that block. So all of them have the same mass, they have the same tension. So that they all have the same length. And in fact, I could rewrite this to get rid of that. These could simplify. So the only thing that can change is the mass, right? The mass of the string is the only thing that could change to make a different fundamental frequency. So the question says, A, what is different about the 4 strings above that result in their having a different fundamental frequencies? And the answer is m, the mass of the string, and this is why. Okay, so actually let's just write this out as F equals 2 over L times the square root of, I'm going to call it T, L over M. And then if I bring this in as L squared, I get F equals 2 times the square root of T over ML. Right? Because if I bring that in, I get ML squared, and then one of those is going to cancel. Okay, so that's that. That's the frequency. A student graphs frequency as a function of the inverse of linear mass density. Will the graph be linear? No. Okay, I'm glad I did this. So this is a linear graph. Y equals mx plus b. So if I have this variable versus that variable, then it is linear. Let's plot, let's write this equation as mass density, inverse of mass density. So I'm going to go back up here and write this. So I'll just use this version. And I'm going to call that, I think normally called linear mass density sigma. Call it sigma. Okay. So let's write this as F equals, I'm going to get everything but the sigma. So I have 2 over L, square root of T, that's it, times 1 over the square root of sigma. That's the linear mass density. This is the same equation as that. And so here if I plot this, y equals mx, then the slope should be this, and that would be x. Okay, but if they plot 1 over sigma, this is not proportional to 1 over sigma, it's proportional to 1 over sigma, the square root of 1 over sigma, or 1 over the square root of sigma. So it's not a linear graph. If I plotted 1 over the square root of sigma, that would be linear. I'm not too happy with that answer, but okay, let's just see one more part. Okay, part C. The frequency of an oscillator connected to string D is changed so the string vibrates in its second harmonic. Okay, I'm not 100% sure, but I think the second harmonic is this. So it goes like this. So it's one wavelength. On the side view of the string, mark and label the points. I should have drawn it more carefully. Have the greatest average vertical speed. So this is vertical speed of 0, vertical speed of 0. So these would be the greatest vertical speeds. That's that. That's kind of dumb. And that's the end of the exam. Stop. So I'll stop. And that said it would take 13 minutes, and I took 7. Okay, so I'm doing pretty good. Okay, so that's that. The whole playlist is down below. If you want to look at them, have at it. I'll talk to you later.